Hello dear students, in this subject groundwater assessment and development. Today we'll continue that chapter, first chapter groundwater hydrology, and already we have covered this up to this storage coefficients. Okay, today class will discuss about groundwater basins and this basins and Darcys Law. Permeability we'll discuss more in next class. Permeability already we have covered some part, and some part we'll cover in the next class. Okay, so in today's class we'll continue. We'll discuss this groundwater basins and Darcys Law. What is this groundwater basins? Groundwater basins is nothing but the alluvial aquifer or the stacked series of alluvial aquifers. Okay, you can see here it's like the river basin. Here you can see these are the boundary of this groundwater, a definable boundary, a definite boundary you can say. And here this is the catchment area of this groundwater. This is the catchment area. This is the catchment area of this. Because when rainfall occur here in this region, the water will flow here in this direction, here in this direction. So there will be flow to this stream, this large stream. I mean, there will be small streams here. And this river will form river formation that will occur from the hills. From the hills, the river is originated. So during the flow, there will be infiltration and there will be vertical movement of flow towards this groundwater table. From not only from this vegetation, from this area, from this land, but also from this river. There may be contribution from the river to the groundwater table. Okay, so this boundary, this is the groundwater table. Groundwater table GWT. Okay, this is the groundwater table, and this is the bottom layer or the bottom boundary of the groundwater basin. Okay, so it's like a river. There is a river, and this is the whole catchment area of this river, like we discussed in the first class. That this is the whole basin. You can say the whole basin of this river. Okay, then this river is maybe joining to the sea, to the joining to the sea, like here Manadi River, Ramani River, they're joining to this Bay of Bengal. Okay, joining to this Bay of Bengal. So here groundwater subbasin means the part of this whole basin. The part of the whole basin. Let there is small streams joining here. Okay, and let you consider only this. Let you consider this. This is the outlet. At this point, what is the catchment area? So at this point, the catchment area will be like this. So this catchment area, you can say, as a subbasin of this whole river basin. So this is the subbasin of the whole river basin. Similarly, in case of groundwater, there will be subbasin of groundwater, means part of the groundwater basin. Part of the whole groundwater basin is called subbasin, groundwater subbasin. Like here, this is the, if we take this part, this left side and this right side, okay, its flow is occurring here. If we divide this, so here, if the water will there will flow in this region. This left part, we can say this is the left side or left subbasin, or you can say the subbasin of this whole groundwater basin. This is the right part of this this basin, groundwater basin. So this subbasin, it can be created using geologic and hydrologic barriers. Geologic barrier, hydrologic barrier, institutional barriers. Okay, so there is no particular definition of this subbasin. It's just any part of the basin. Any part of the whole basin is called subbasin, like in a river. Okay. Next is the different aquifer layers in groundwater basins. Aquifer layers: shallow aquifer, principal aquifer, and deep aquifer. Shallow aquifer, it presents just below the soil layer, just below the groundwater surface, ground surface, and the thickness is very less. It can give water, okay, for temporarily it can give some water. Okay, some water can be extracted from the shallow aquifer, but the water is usually extracted from this principal aquifer. Principal aquifer, the storage is more. This depth or the thickness of the aquifer is more. So this is usually considered as the groundwater storage, and it can be extracted easily. However, in deep aquifer, it cannot be extracted easily because the depth is very high. So, although it contains a huge amount of groundwater storage, okay. So this deep water storage, deep water aquifer, is not usually used for the extraction. It depends upon the principal aquifer. The principal aquifer thickness is less. Okay, the sufficient thickness is not available if the water that we are extracting that is not sufficient. Okay, then we may go for this deep aquifer. Okay, and the recharge, this deep aquifer recharge takes place from this principal aquifer. There may be flow from this principal aquifer to the deep aquifer, and there may be flow from the deep aquifer to the principal aquifer. Okay, and usually the shallow aquifer, it is, you can say, unconfined layer, because it's from the groundwater surface there is a impermeable layer here at the bottom of the shallow aquifer. Is an impermeable layer. So this is called unconfined aquifer. And this principal aquifer and deep aquifer is called, both are called confined aquifer, because they are confined by this impermeable soil layer, impermeable rock layer. Okay. So this is about the aquifer layers in groundwater basin. Next is the Darcys Law. Darcys Law. Okay, this law is developed by Henry Darcys, okay, a French hydraulic engineer in 1856. Okay, he conducted many experiments. Okay, experiments on this flow of water through these horizontal beds of sands. The bed of sand, he conducted many experiments. And it is used, which is used for this water filtration in the city of Dijon in France. Okay, so from this his experiment, he concluded that, okay, he found that this volume of water per unit time, which is called discharge or rate of flow, is directly proportional to this Q is directly proportional to the cross-sectional area perpendicular to the flow, means cross-sectional area of this soil mass, inversely proportional to the length, of the soil mass, and the proportional to the soil loss of head over distance L, loss of delta H over this length L. So this, if you combine this, you will get discharge is directly proportional to this delta H by L, delta H by L into A. Okay, so if you combine this, the discharge, which is directly proportional to cross-sectional area and which is directly proportional to this delta H, the loss of head, and inversely proportional to the length of the soil mass. It means if the length of the soil mass increases, then the discharge will decrease. And if the loss of head is more, the discharge will be more. The rate of flow will be more. And it also depends on the cross-sectional area. If the cross-sectional area is more, then discharge will be more, the Q will be more. So combining these three principles, okay, it can be written as K into A into delta H by L, where K is called hydraulic conductivity. The K is called hydraulic conductivity that we discussed in the last class. Okay, in the last class we discussed about this hydraulic conductivity, which is equal to the intrinsic permeability into there is one formula that we discussed, intrinsic permeability into specific weight divided by dynamic viscosity. This formula, the K is equal to small k, which is intrinsic permeability, into specific weight, which is rho g divided by mu. Mu is the coefficient viscosity. So this, you can write this small k. Small k is the intrinsic permeability, which is CD10 square. CD10 square, usually CD square, or you can write CD10 according to Huygens formula. Huygens in this Huygens empirical formula, CD10 square. CD10 D10 means the size corresponding to the 10% final. 10% final. This K into this is rho G divided by mu. So this rho G, if you put here in Q, it will be small k into A. Okay, this value I am putting small k into rho G by L. Here I am writing. It will be small k rho G by mu. Rho G by mu. Rho G by mu into A into delta H by L. Okay, so this rho G into delta H is nothing but the pressure drop. Rho G delta H rho G H. Pressure drop divided by mu into A by L. So here K into A double delta P divided by mu L. So here negative signs refers to this change in pressure, decrease in pressure. There is a decrease in pressure from inlet to outlet, so it's taken as negative, minus symbol. So minus K delta P divided by mu L. Q is the total discharge. The small k is intrinsic permeability, or you can simply say coefficient of permeability. Coefficient of permeability means it is small k. It's not that hydraulic conductivity, which is this coefficient of permeability means intrinsic permeability. A is the cross-sectional area of the flow. Pressure drop, which is rho G, rho G H delta H. That is delta P, and mu is the coefficient of dynamic viscosity. L is the length of the medium. This porous medium, that soil medium. So this is about the Darcys law. And this, if we calculate the velocity in this soil mass, the velocity is equal to Q by A, discharge per unit area. So discharge per unit area, you can calculate K delta H, K dH by dL. You can write dH by dL at the delta H by L. Okay. We can write anything. Means delta H by L you can write, or dH by dL you can write. Okay, that's nothing but the hydraulic gradient. Delta H by L is hydraulic gradient, or dH by dL is the hydraulic gradient. So this V, which is discharge per unit area, is called Darcys velocity, or it's called specific discharge. So Darcys velocity assumes that the flow occurs through the intersection of the material without regard to the solids and pores. So Darcys did not differentiate this pores and the soil mass, the solids. However, the flow cannot occur through the solids. Flow can only occur through the pores. Therefore, since flow is limited to the pore space only, that's why that velocity, if we consider the velocity through pores only, then it's called average interstitial velocity. Average interstitial velocity, BA. It is also called apparent velocity. It is also called apparent velocity. It's called average interstitial velocity, which is Q by theta A. Q by theta A. So theta is nothing but the porosity. Theta is nothing but the porosity. Okay, so if we will not differentiate this pores and the solids, if we consider overall velocity of this soil mass, which is taken as discharge by area, we consider discharge by area, then it is called specific discharge, or it is called Darcys velocity. If we take Q by theta A, that means it is the velocity, it's average interstitial velocity. Theta is the porosity. Okay, so this is about the velocity, Darcys velocity. Next is the validity of Darcys law. When Darcys law is valid, whether it is valid in all types of soils, whether it is valid for all types of flow, Okay, so first you see this Darcys law is valid if the flow is, through the soil is laminar, and the flow of water through soil depends upon the dimension of the particles. In fine-grained soils, the dimension of these voids or interstices, okay, is very small. In the fine-grained soils, these voids are very small, so flow is laminar. It is compulsory laminar. Flow cannot be turbulent. So in coarse-grained soil, some coarse-grained soil, the flow is also laminar. However, if very coarse, if the particle size again increases, it's very coarse particles, then it becomes turbulent. Okay, like in gravels or boulders. Okay, when the soil size is very more, means the very coarse, the flow will be turbulent. So when soil size is less, the particle size is less, the flow is laminar. When particle size increases, the flow changes from laminar to turbulent. So in case of turbulent flow, this Darcys law is not valid. So flow through soils, the flow is laminar if the Reynolds number is less than unit, less than 1. Okay, so for soil, flow is laminar if the Reynolds number is less than 1. So when Reynolds number is less than 1, it means when flow is laminar, the Darcys law is valid. As for Allen Huygens, okay, it did many experiments and developed empirical equations like intrinsic permeability of the CD10 square. The maximum diameter of the particle for the flow to be laminar is about 0.5 mm. He conducted many experiments and found that the 0.5 up to this about 0.5 mm particle size flow is laminar. Okay, this since this laminar flow can occur only for small these fine-grained soils, this Darcys law is valid for clays, silt, and fine sands. In coarse sand, gravels, and boulders, when the particle size increases, the flow becomes turbulent, and Darcys law will not be applicable. So to validate this Darcys law, the relationship between the velocity and hydraulic gradient should be linear. The hydraulic gradient and this velocity is q by a, that already we discussed, which is k into delta h by L. So this is hydraulic gradient. So this velocity should be directly there should be linear relationship between velocity and hydraulic gradient. Then Darcys law can be valid. In another case, when the soil size is very less, means very fine, extremely fine-grained soils like colloidal clay. Colloidal clay, this type of clay, the soil size is very less. If the pores are very small, interstices very small, the velocity therefore very small, I can say approximately zero. Approximately zero. This flow is hardly possible in this type of clay. So when velocity, the flow is hardly possible in that soils, the Darcys law cannot be applied. Okay, so Darcys law cannot be applied if the soil is very fine. This you can say this plot shows that specific discharge and the hydraulic gradient. Okay, velocity and the hydraulic gradient k into this delta h by L. And here you can see this Reynolds number when it is less than 1. Remember this Reynolds number when it is less than 1, the Darcys law is valid. Okay, and this Reynolds number can be extended to 10. Can be extended to 10. Okay, and if the flow is laminar, condition is that flow must be laminar. If the flow is not laminar, flow is turbulent after Reynolds number less than let 5. After 5, Reynolds number, flow becomes turbulent. So in that case, after 5, cannot apply the this Darcys law. The Darcys law can be applied up to Reynolds number 10 if the flow is laminar. If the flow is laminar. Okay, so beyond 10, whether flow is laminar or turbulent, in this case, the Darcys law is not valid. Okay, so Darcys law to be valid, the flow must be laminar, and if Reynolds number should be within 10. If it is less than 1, then there is no question. Flow must be laminar. There is flow cannot be turbulent. Okay, so in that case, Darcys law is valid. But 1 to 10, it depends upon the whether it is laminar or turbulent. If it's laminar, then valid. If it's turbulent, not valid. And more than 10, whether it is flow is laminar or turbulent, the Darcys law is not valid. Okay, so in this region, here you can see, in this region, you can see more than, Reynolds number is more than 10. And the flow is changing from laminar to turbulent. You can see the nonlinear. Okay, there is linear relationship. Whether it is laminar, but if there is nonlinear relationship. Another condition is that for the Darcys law to be valid, the velocity should be linearly related with this hydraulic gradient. Okay, so for this linear relationship, the Darcys law is valid. First, Darcys law is valid for linear relationship for laminar flow, and the Reynolds number must be less than 10. Okay, here you see that Reynolds number is beyond 10, and here flow is changing from laminar to turbulent. So you can see this. You can say this is the transition region. So in the transition region, it's not valid. And here, when Reynolds number is more than 100, the flow is turbulent. Okay, here it's not valid. Okay, so this is about the validity of Darcys law. Here another picture, you can see the pressure current versus velocity. Here this is called pre-Darcys zone. Pre-Darcys zone means pre-laminar, and the Darcys zone is laminar. Here, when the velocity there is no linear relationship. There is a non-linear relationship between velocity and this hydraulic gradient or pressure gradient. Here you can see this non-linear relationship. So in this region only there is linear relationship, so it is called Darcys zone. Or here only Darcys law is valid. Here Darcys is not valid. Here it's not valid. So at last, let's discuss about this assumption of Darcys law. Okay, then we'll complete the class. The soil should be saturated. The flow through the soil is laminar, should be laminar. The flow should be continuous and steady. And the total cross-section area of the soil mass is considered. Total cross-section area of the soil mass is considered. Okay, since Darcys did not differentiate the pores and the solids. Okay, the temperature at the time of testing is 27 degrees Celsius. Okay, since this temperature changes the viscosity. Temperature changes the viscosity. Okay, the maybe in that case, Darcys law may not be valid, since the test means the experiment is conducted considering the temperature is at 27 degrees Celsius. What about near about this 27 degrees Celsius? As far as this viscosity is not changing. As far as the viscosity of the fluid is not changing, Darcys law can be applied, even if temperature changes. So when temperature changes, let's consider you have not taken water, you have taken any other fluid, and if you decrease or increase temperature, then there will be variation of viscosity. Okay, so in that case, the Darcys law may not be valid. Since in general we are considering water, as far as civil engineering concept, the water fluid is water. So if your temperature changes, then viscosity, there are no more changes in the viscosity of water. So for different temperature also, the water can be, the means Darcys law can be valid. Okay, so this is about this Darcys law and groundwater basin for today's class. Okay, this much. In next class we'll discuss about the permeability. Thank you so much.